a photo on the online system. I'll give you a bonus point for everyone who uploads a photo. Maybe that's a better strategy. I know that's going to work a lot better. All right, so my class will be on exoplanets. It will be fairly general. I think it will be quite different. I quickly watched a little bit of the video of Arun's lectures. It will be quite different from that, which some of you may like and some of you may not. Some of you may be relieved, I don't know. So my course will be much more observational, so talking about the data, much less about physics or mathematics, which, you know, maybe it's good or bad, I don't know. The reason is exoplanets are very recent and it's very hard to, well, a lot of things move with data. So that's what it's going to be about. So maybe I will start with a cartoon that it's an XKCD cartoon. Maybe someone knows it. The cartoon that came out in 2012, sort of as I started my PhD, so about 5 years ago. And so at the time, it said these are all 786 known exoplanets to scale. And then this bit here, that's our solar system. So that's the 8 planets in our solar system. And then it says, well, the rest of these, they orbit other stars, and they were only discovered recently. Most of them are huge, because these are the kinds we learned to detect first. But we're finding that the small ones are actually more common. And then it says we know nothing about what's on any of them. With better telescopes, that would change. And finally, it says this is an exciting time. And so at least of that thing, I hope to convince you this week in 5 lectures that this is indeed this exciting time where we're finding new exoplanets, where we're learning about them, where we're also starting to find the small exoplanets now, not only the big ones. Things have changed in 5 years. And we're actually starting to learn about their properties and, you know, what's on them and what they're like. So, you know, I hope at least most important message of this whole course is that this is an exciting time for exoplanets. So, why study exoplanets? I'm going to ask to you, no wrong answers. Why would you or should someone study exoplanets?
Maybe it's a good way to, you know, to identify and learn how to make like a classification.
Yeah?
Of how common or uncommon can our own solar system be?
Okay. How common is our solar system? That sounds like a good reason. Anyone else?
I would think like it's of scientific interest, like detecting how other planetary systems form and develop, like in different stages. Like we can find some system that is in a previous stage than ours is, or a more advanced stage in our solar system is. So that might tell something about our own solar system or our own planet even.
Yeah. So learning about formation of our solar system and about evolution by studying other stages in exoplanets. Yeah?
To find life?
To find life, yeah. That was not number 1, number 3. Yeah, that's a good one. Anyone else? Anything else? Any other reasons? Sorry? Characterizing new worlds. Yeah, pretty good. Anyone else? No, there's no wrong answers. I'm gonna like keep asking until I hear people that have not answered things yet, because we're not gonna spend the whole week with only the same people answering. So go ahead.
This might be a little too hopeful, but maybe to search somewhere where we could live, when we have interstellar travel.
All right. No. Yeah, that's hopeful, but hope is good. So yeah, to find a place to live. For us, once we destroy the Earth or something like that, that could be a good reason. All right. Any other reasons? Why are you taking this course? Because you have to, maybe. Also a reason to study exoplanets, I guess. Anything else? What do you want to learn?
it's not like too hard to think about it. Maybe if we live for 1,000 or 2,000 more years, these are like the first baby steps into like colonizing new worlds.
Colonizing the world.
You know,
All
like
right.
little baby.
So we don't
steps.
just want to find aliens now, we do want to
Yeah, maybe.
destroy them all. All right. That sounds fun. Maybe it's better to find them before they find us.
Yeah.
Anyone else? Because it's exciting, yeah, good one.
Maybe also to search resources.
To search resources, yeah, to get.
We don't have to go there and eliminate the aliens. We can just take a little part of the resources and use it here on Earth.
We
Maybe,
got
I don't know.
trade with the aliens, pretty good. All right, so I think, well, I'm going to categorize the purely scientific reasons to trade with the aliens and finding that not so on. I think there is a broad set of questions that relate to habitability, aliens, extraterrestrial life. That is a lot of the reason why a lot of people look for exoplanets or are interested in exoplanets. So that has to do with answering questions like, are planets common? You know, is there a lot of planets like Earth? Are there a lot of planets in general? Are they, if there are planets, how do they look like? Are they all Jupiter, gas giants, or can there also be Earths? Things like that. And then secondly, can we then also learn about maybe their atmospheres, their compositions, and whether they actually have life? And so eventually, we do want to study and find out if planets may have life. The last question, do they have life? We're not quite there yet. We're not actively studying anything much that will tell us if a planet has life. But the first steps towards it, which is finding out how many planets there are, finding them, and trying to understand what they could be like, and developing the techniques to eventually find life, is the kind of things we are doing today. And then the second, I guess, category of questions is about formation. That was also one of the things that was mentioned. So how do planets form? Is there something specific about the solar system and its formation? You know, do all planetary systems look like the solar system? With 8 planets in a flat disk, sort of all in the same plane, and with the rocky planets on the inside and the other planets on the outside. Is that generally true? Does that work? Are there other planet systems like? Can you have planets around binary stars? Can you have very strange kind of planets? What about their orbits? Are they circular? Are they eccentric? What about the rotation of the star relative to the planet? And what can we learn not only about the other planets, but also then about our own solar system and how we formed as well? And I should add here perhaps the evolution question as well. Like we can try to understand, for example, can the solar system survive once the sun will become a red giant? It will grow. Will that destroy all the planets? Are there any planets around red giant stars, for example? It's a question the answer is yes. Can we find those? That's the kind of things, you know, I guess broadly these two categories are why most people actually study exoplanets. Beyond, of course, the general scientific idea that it's interesting to find out, you know, what we don't know yet about the universe. And so that's where we're at. What is an exoplanet? I put up this nice picture. This comes from online. This is the kind of images that get made by astronomers, or at least press affiliates of astronomers. This gets released. I don't even know which planet this was supposed to be. But yeah, this is, you know, it looks pretty nice actually. You know, there's rocks. You can't really see it very well, but there's, I think, 2 stars here. Some kind of clouds. Looks a bit like, I don't know, Hawaii, I want to say. Looks like a pretty cool planet. But of course, it's not really how we actually see these planets at all. I looked for more images. There's more. Like there's another one here. Same, find it online. This was used in a press release for another planet. Again, it looks pretty cool. This is like lava here and rocks. And then I guess the star and another star, 3 stars. Another planet up here. It looks pretty good. I don't know if it's true or not. It's probably based on something, but maybe not on that much. But this is the kind of things you often see in the press about planets. and they shape a little bit of the idea of what a planet is like, and it makes people dream about other planets, which is probably good. It sometimes gives people the wrong impression about what astronomers are doing, because we're not really making any photos like this. But so, second question should say, what is an exoplanet? Again, no wrong answers. So tell me, what is an exoplanet? What do you think an exoplanet is? Like, how would you describe an exoplanet in your own words? Anyone? A planet orbiting another star, so not around the sun, somewhere else. Yeah? Pretty good. Anyone else?
Or maybe isn't it just a planet that isn't in the solar system?
Planet that's not.
It doesn't have to orbit around a star. It can be an errant planet. No.
Yeah. So if it's lonely and has no star, still a planet. Yeah, that's a good way to do it. That's not how we would do it in the solar system. You know, we call Jupiter a planet because it orbits the sun, and we would not call it a planet if it didn't. And we don't call Pluto a planet because it hasn't cleared its orbit or something like that. So by your definition of exoplanet so far, Pluto should then be a planet, I guess.
One thing, is necessary to define an exoplanet that this planet orbiting on a star, or is not necessary? Because there are, or could be there, a planet that is not orbiting on a star, and there are no seen.
So you're saying planets that have no stars are still planets? I don't know. It depends, I guess, what we want to, what should a planet look like? Does it need to have a star for anything? Yeah. At least in our solar system, we're pretty strict. We kicked out Pluto as not being a planet anymore because, well, because of its orbit. Although, purely it's a round object, more or less, orbits a star. So who thinks a planet should orbit a star, and who thinks it should orbit a star? Any hands? Everyone else? No star? No star's fine? All right. It's up for debate. So generally, we're going to talk about this here. Generally, when we talk about exoplanets, we're probably going to mean things that do orbit other stars, but we're not going to be very strict. So if we find things that are not orbiting a star, we're probably still going to call them exoplanets. And then I guess the other thing, no one has talked about this yet. What about how big does it have to be? Big enough. What does that mean?
I think that size is related to this, what you call it, hydrostatic equilibrium, for it to be round.
For it to be round. So big enough to be round?
Yeah.
Right? Anyone else? Does it? Yeah, good question.
Doesn't it have to be big enough to be round? Like, do we actually measure exoplanets' roundness?
We definitely don't really measure the roundness, no.
Like,
That's
not
a good
measure, but can we see it? Like, can we,
That's
like,
a
the
good
ways we
argument.
detect exoplanets let us know if they're round enough?
So, okay. So two sides. One of you is going to be wrong, I'm sorry. So you're saying hydrostatic equilibrium has to be round, but you're saying, well, there's a problem because we can't really measure that. So how are we going to know? So shouldn't we just say basically it's fine because we don't really know how round things are, right?
Yeah.
What do you think? This camp? Anyone? Or this camp? Okay, you have to choose. Who agrees with, what's your name? Miguel. Who agrees with Miguel? Anyone? No one? Who agrees with Jeronimo? Oh, you do have to choose. All right, that doesn't work. All right, again. We need to see like everyone's hands. Okay, so who agrees with him?
I think that Miguel has a point, but
He has a point.
maybe we could deduct that the planet is round by the amount of dim that produces in the star.
Okay.
Because there's a limit that an object has in space to become round, doesn't it?
So you're saying, well, if we detect things that are big enough, we know they probably have to be round anyway.
Yeah.
So we're fine. All right, now I have 3 sides. You agree with him? All of you agree with him. All right. Well, so I'm going to say it has to be small enough, but we don't really care about minimum size. So I guess you were right. We're generally a lot less strict in our definition of exoplanets today as we are in our definition of solar system planets. And I guess the main reason is that in the solar system we more or less know what all the planets are like. And so we can say those things like it has to be big enough to be round because we do want to exclude all the comets. And we don't want to say that they are planets because they're irregularly shaped objects. And you may argue they're planets too, but if they were around another star, we'd probably call them exoplanets. Because we're not that strict. So generally, you're right, we don't really impose much of the rules. We don't really impose they have to be around another star. We're just going to say everything that that we can think of as planets that are not in our solar system are exoplanets, and we don't really have a very strict definition yet, which is, I guess, in a large part driven by the fact that we don't quite know what kind of things to expect. We have one hard limit, though, which is about how big it can be. It can be too large, because at some point, if things get too large, they're just going to be a star, and we definitely don't want to have that. So we want to exclude stars, and more strictly, we're going to exclude even brown dwarfs. So brown dwarfs that burn deuterium, what brown dwarfs are? So they burn deuterium. So that's also, once there is nuclear reactions in some way, no more planets. And the way we do that is by making a cut on mass, mostly. Or if things get too massive, 13 Jupiter masses, we say, well, that's it. That's not a planet. Yes?
We were like saying if we can get a round exoplanet or something like that, is there actually any exoasteroid detected? That small?
See, it's a slightly tricky question. Well, it's not very clear. We have hypotheses about it. There's one of the stars that made a lot of news. You might have heard it about alien megastructures, stars, that kind. More like common interpretation, I guess, is that there may be a lot of asteroids there. So we see a lot of drops in light curves that could be explained by perhaps a lot of asteroids or ring systems like that. It's not super clear. We're not quite sure if that's what it is. So the answer is maybe. What we are sure of, though, we have found some planets that are disintegrating, I want to say, so that are losing some of their atmosphere or some of their material. They're very close to the star, and they're losing part of their atmospheres. So they have like a tail of atmospheric material following them in their orbit. So, yeah. And generally, even those things which seem to be exoplanets that are being destroyed by their star, we still call things planets. And people do look at, exocomets or things like that. No clear detections. I mean, your next question should be, what about moons? Have we found any moons? And the answer is also no. At least no one has found a moon that I would convincingly believe in. Some people have claimed some things that might be moons. So the answer is also no there, but that's the kind of thing we're probably going to find at some point. It's just not that easy to do, because moons are small. But, that's, we are.
In a transit, when you see like this light curve of a transit, you cannot see like a zoom a little bit more and see like a transit in the transit. It's like a way to find an exomoon or something, or? People
have, people have suggested different methods with transits to look for moons, including these kind of things like asymmetries in transits and so on. And people have looked, but not found. But the problem is, well, we should talk about this more when we actually talk about transit. But just to answer your question, the problem is that the transiting systems we find are typically close to their star. And that's not exactly where you would expect to find moons. You expect to find moons around Jupiter-like objects, far away, big planets. That's the kind of moons you would be able to detect, but that's not the kind you can find in transit today. And the moons you expect around small objects close in, like the Earth, they're probably hard to find. They're hard to see because they're too small. So, we might just not be there yet with the data to actually see them. That doesn't mean they're not there. All right. So planets, like I said, everything that's small enough that doesn't have to orbit around the star, but I think for the whole course we're going to talk only about objects that actually orbit other stars. And so, masses are quite different between different objects, even within the solar system. So the Earth and Jupiter are different by a factor of 300 or so in mass. So, Jupiter is really a lot more massive than the Earth. So we have this quite big diversity in masses. And then, make it even 13 times larger, and then you have brown dwarfs, then you have fusion of elements, and then we stop calling things planets. But obviously, there is a big difference between planets like Jupiter or planets like Earth in terms of what they would look like, what they're like. Earth has rocky surfaces, Jupiter does not, but that's all planets. All right, just one technical point about how we name them. We generally name planets after their star, and then we use the letter B. So if I have a star called Alpha Centauri, then I would call the planet Alpha Centauri B. First planet I would find, normally. Like small letter B, because capital B's or capital letters are used for stars. So if we have a binary star, right? If we have a binary star, then we would typically call one of the stars A and one of the stars B. Okay? So we have Alpha Cen A and Alpha Cen B, capital A, capital B. That's two stars. If we have a planet, we will call it by the letter B, the first one, small b. We don't use the small a, which seems like an error given that we do use the small a for the star, the capital A for stars in the binary. I guess it was to avoid confusion with the star and the planet, but it's kind of confusing now as well, because now you can have like Alpha Cen A, that would be the first star, but then the first planet around that star would be Alpha Cen A B, and then Alpha Cen A. But yeah, that's how we're going to be stuck with it. So we start with B. That's this kind of astronomer convention that in a few hundred years people are going to be complaining about, but that's how it's going to be. And then, if we have more letters, we just first use the star and then the planets. That's not very hard. And then often stars do get renamed after planets are found, especially if they have hard to remember names. Alpha Cen is fine because everyone knows Alpha Cen, but if we have a star called HD blah blah, HD telephone number, HD 109 blah, that's kind of confusing or annoying, and not everyone likes that. So people often rename the stars, and then usually this is the most common question you get from non-astronomers when you say you found planets. Can you name them? Well, not really. Usually we name them after the instrument. So if we use Kepler to find planets, we will now say we have found Kepler number 10, so we call it Kepler 10b. Planet, 10th planet discovered with Kepler, first planet B around that star. And if we have more planets, we're going to call the next one Kepler 10c, and the next one Kepler 10d, and so on. Does that make sense? It's not just a simple technical point. I'm going to immediately warn you that I'm going to be very inconsistent when I speak about planets. And so sometimes I'm just going to say Kepler 10 when I really mean Kepler 10b. So Kepler 10 technically should be the star, and Kepler 10b should be the planet. I'm going to be inconsistent, and sometimes I'm going to just say Kepler 10 when I really mean the planet and not the star. You're going to have to accept that that's how it's going to be. But yeah, so generally, normally you should use the letters for the planets and just the Kepler 10 for the star. Yeah.
So if there's a second planet found around Kepler 10,
yeah,
you call it Kepler 10c.
Yeah.
Even if it's for some reason on the inner part of the orbit of Kepler B. So
yeah.
it's named after the date it was detected. It doesn't depend on the geometric position of around the sun.
Right. I'm going to try to use this. So you're right. So okay. So let's say we have a star. This is my star. This is how stars look like, right? So originally it's named HD 10923 or whatever. We find it with Kepler. We find one planet. Looks like this. That would now be, we find it with Kepler. The next one to find with Kepler today would be something like Kepler, I don't know, what we're at, 2000 or something like that. 1500 maybe. 1529 B, right? And so the B is this planet, and Kepler 1529 is just a star, or also HD, whatever it was before. Now if you find another planet that looks like this, you say inside, yeah, we're still going to call this one C, and this one is still going to be B. Ideally, this is super annoying though. I mean, ideally this never happens, because it's annoying normally, but if we find everything together, then that doesn't happen. Then we have a star, and then, you know, let's say 3 planets, and we're going to call them B, C, and how do I write it, D, and then D. Normally that's how it would be, unless, you know, the first one wasn't found, and then, you know, then you end up in this annoying situation. There's not much to do about it, because, you know, once you found one and you call it B, it's really hard to then say, now this is no longer B, this is going to be C. Because, you know, people have already written about this one planet, already called it something, it's hard to then, you know, it's hard to fix after the fact. It doesn't happen very often, because usually the inner planets are the easiest to find, and the outer planets are the hardest to find. So normally we typically find the first ones here, and then later we find things more far out. But yeah, it does happen, and it can be a little confusing.
I have a question. What happens if the solar system has more planets than letters? I don't know, we have 50 planets.
Good question. So that hasn't happened yet.
No.
So that's not a problem. I guess we're going to use double letters, so we'll call them AA and AB and AC, like
Okay,
multiple
that
small
makes
letters.
sense.
Which sounds like the solution I would use. But I think it's the most planets we've found so far is something like 8 on one system. So not a problem.
So
but yeah.
we could say that the solar system, our solar system, has the most planets yet.
Well, we also have 8, so if you want to call Jupiter planet 9, whatever. But yeah, I'm not saying that's true in reality. I'm saying that's true in terms of what we found so far.
Okay.
Yeah.
Yeah, that's all. Thanks.
If we were to apply this like to our own solar system, or if we say like somebody in another solar system sees us and uses the same like notation, he would call like, I don't know, Earth would be like Sun, D, and I don't know, is there any plan or something like to call the moon of a planet in this notation, or?
The moons?
Yes. Is there any idea?
Good question. I guess technically,
like just in case.
yeah, I guess technically this would also like force us to use like double letters again. I guess we would say, I mean, that's what we're doing right now, right? With binaries, we say if the planet's around binary star number B, then we call it BA. So we probably have to use a different symbol for the moons. I don't know if anyone's thought about it. We haven't found any moons, so it's not a problem. But yeah, I mean, it's just a technical point, just so we know when we talk about planets how we do it. All right. Just want to give you a slight historic context. It's not a history class, but I just want to put up, like, for thousands of years, people have thought about whether there are other planets or not. So it goes back to, for example, before Christ, Aristotle said there cannot be more worlds than one. That was definitely wrong. Epicurus said exactly the opposite. There are infinite worlds like ours. Infinite is also a large number, so that's probably also wrong. Chinese philosophers said, you know, it would be unreasonable that beyond ourselves there would be nothing else. That sounds right. At least today it sounds right. And then, you know, this is a few hundred years ago, there are numerous suns, numerous Earths that revolve around, and that was pretty much spot on. But I just want to say that despite this, you know, philosophers' claims, there has been essentially zero actual data to support any of these claims for well over 2,000 years. And it has taken us until the last 20, 25, maybe 30 years for us to make any actual progress. So just to put this in the big perspective, as humanity, people have wondered for a long time about stars, about whether they may have other planets, and so on. But it's only, kind of since all of us were born that we've actually made any real progress. So we're actually kind of the first generation that has actually started answering any of these questions. And I mean, not all of them are answered yet, but we are, it's all very recent. And I guess this course is going to reflect that kind of thing. A lot of the results I'm going to show you are not set in stone. They're not quite clear yet. Many things are quite recent, and so a lot of results are going to be the way we see things right now. And if you take the same course in a few years, you might get some somewhat different results. So it's going to be a lot of recent research and results. So just the way it is. If I had to show you only things from 30 years ago, then this course would be done right now. All right. So I want to show you this movie that shows you, it's going to be a little hard to see, but it shows that exoplanets were only discovered very recently. This was made by a friend and colleague, Hugh Osborne. I'm going to try to show you here. All right, so, this shows you the amount of planets discovered over time. So we're in the 1700s now, 1800s, and you see there's 8 in the solar system. And then, we just wait. Not that much happens until somewhere in the 1900s. We're going to add Pluto. Yeah, Pluto, somewhere down there. And then we wait and wait and wait and wait until very recently. And now we're going to start finding the first new exoplanets. And now things are going to go fairly quickly. You're just in, 2000 or so. We're going to start finding a few dozen. And then things continue. And we're going to start finding them pretty rapidly. And the different colors here, I'm going to come back to it, so don't have to worry about it. But there are different ways of finding them, showing that also there's different ways of actually finding the new planets that all have their own advantages and disadvantages in a way. So now we're at 600. This is where my cartoon from earlier was, at around 800. And then things really explode in the recent years, where right now we're sort of at, I was going to stop here at about 3,000. So a lot of planets are going to just play again. So a lot of planets very recently. In the solar system, by the way, this also, I have to look this up. But like Uranus was discovered in 1780 as number 7 in the solar system. And then Neptune in 1846. And then in 1920 or something like that, Pluto. So then we were 9. And now we're back to 8, I guess. We just threw it out again in the 2000s. But that's how it was. And so everything is essentially discovered after 1990. I want to often say the first planet that I would call a clear exoplanet was 1995. So 22 years ago. And since then, a lot of progress has been made. We found a few thousand planets at least. And we're starting to also understand what kind of planets we're seeing and learn their properties. But just, and a nice cartoon to show you that this is all extremely recent stuff. All right. All right, so I know we've already discussed it, but I just want to, now that we've actually talked a little bit about exoplanets, show you again what this course looks like. So there will be 5 morning lectures, which are going to roughly cover these topics, maybe not exactly in this order or in this like course by step-by-step way. But so this is today, history, introduction, and rate of velocity planets, which is one of the ways to find the planets. And then we're going to move on. Maybe not entirely yet tomorrow morning, but at some point maybe tomorrow, to transiting planets, which is what's going to be the main part of the course. For one reason, because that's what I know the most about and like the most, but also they have been the most prolific way of finding new planets. It has been the most efficient way, and it's the one that allows for the most understanding of planetary systems as well. So there's just the most to be done with transiting planets that we cannot do with the other ways of finding planets today. And then, so the rest of the lectures will essentially be about what we can learn about those planets. So it will be a bit about dynamics, about how many planets there are and their constraints on their structures and so on. And finally, this will be Monday morning. It will be about atmospheres, habitability, and so on. So that's the morning lectures. And then, as I said earlier, there's afternoon exercises. So there will be 3 different ones. But you'll have 5 afternoons to work on them. So number one, that's what you're going to get today. This will be on introduction exercise, I want to say. It's mostly about the different methods and how you're getting a feeling for what you can find with which method and so on. So this will be fairly straightforward exercises to get a feeling for how do the methods work and what do they look like. You might have to make a few plots in Python or anything you choose, but nothing very programming, mostly just trying to get a feeling for the data. And then there will be 2 data exercises where you're going to get some data and you're going to have to look for the planets. The data is going to be fairly clean and nice. It's not completely raw and difficult. I promise there are planets in the data as well. That helps a lot because usually you have to look for thousands of stars before you find any one planet. Makes it a lot harder. In this case, you're going to have, you're going to have one data set, one planet. Makes it easier. So one is about rate of velocities, and one is about transits. All right, so these are the things you will have to hand in, and then you'll get some kind of grade. I'm going to repeat what I said earlier. Don't worry about your grades or something like that. Please do try to use this course and this exercise as a way to learn something and not as a way to pass a class. If you all try and get somewhere, you will all pass. I promise. So don't worry about it too much. And so don't worry about the grading. Just see what you get and try to actually get something out of the exercises. We're all here to learn. They always say that as a teacher, you learn the most of any course you do. So that's great. I've been learning a lot in the last few days making all of this. So I hope you learned something as well, and don't worry about the grades too much. So the first one, you probably won't have to hand it in today. Let's see a little bit how it goes. So probably that you'll have until tomorrow evening to finish that one, and then you get the next one, and then Monday we're going to the last. And then we'll go through the answers also to see how they can be solved ideally. Don't worry too much about it. And now, as I said, there will be part will just be class evaluation. I'll just grade you based on showing up and asking questions. So ask questions and do interrupt me and on things like that. So don't worry about it too much. Also, the exercises, you'll be free to do them either alone or in groups of 2 people, which you can choose. In some cases, 2 people can help you. If it's programming a little bit, maybe it's easier with 2 people, but you're welcome to do it alone as well. It doesn't really matter to me. But I will be there, and so this is also why you get the class evaluation. If you're a group of 2 people and only one person is doing everything, then that will reflect on the grade as well, but And so I just want to put up a few references here in case anyone wants to learn more. In terms of books, there's 2 big books that I like, that I recommend. One is by Sarah Seeger, and one is by Micah Perman. These are sort of the 2 big exoplanets, general exoplanet books that there are today. And people have a preference usually for one or the other. Both of them kind of cover a lot of the basics of everything for exoplanets. But I don't know, I always liked Sarah Seeger's book. That's what I had in my first class, but people have different preferences. They're pretty equivalent in terms of what you can get out of them. So feel free to have a look at either of those, which gives you an overview. The one thing I should say with Exoplanets books is that things move very quickly, so it's not very good for giving you the latest on any topic. That's the problem with Exoplanets. Any book that's a few years old does no longer have all the recent discoveries. So books like this, both of them actually, will talk about Kepler as this very promising mission with all these great first results, whereas today we found thousands of planets with it, but they were all discovered in the last few years, so that's just how it is. And then there's some shorter, more specific reviews that I like. I'm going to put a few of them online, those that I could find, so you can just get them there in PDFs. So there is this Maria and Correa one. I'm definitely going to put that one online. That's a rate of velocity overview, a little bit of the dynamics, and so on. This one I couldn't immediately find directly accessible, so I'm not sure I can put it online. But it's also a nice review. These last 2 I will put online as well, which are on transits and on dynamics of planets. So I'll try to give you these, which will give you something to read about if you want, which we'll just put on the online system once I figure out how to upload something that is going to be today at some point, I hope. I'll give you some further reading. All right. Any questions on the class and how it will look like? Everything clear? All right. So, I should say, I'm going to try to take like a halfway break at some point today. You know, when I had my first classes and I was a student, we used to tell our professors that it was inhumane to teach for 2 hours without a break. Now that I'm teaching, I don't think it's inhumane, but I'll try to stop somewhere, you know, halfway for a few minutes just to take a quick break. So if I don't, please stop me and say it's 11 or something like that, and I'll just, you know, give a few minutes break. All right, so the first planets, no, I shouldn't say the first planets. Some planets are detected with images. So this is a pretty image from ALMA. You probably have seen it. It's probably like the most famous ALMA result, which shows a star and its disk. It's a it's a star-forming region or something like that. I mean, it's not really a planet. There's no actual planet in this image, but you get this structure here. Like you see these different structures here, which are different pressures and temperatures, which, you know, resemble at least what we think we understand about planet formation, with, you know, different planets forming in different of these bands. That makes sense as how we think planets form. But that's not really an actual image of a planet. But we have a few. Not very many. But there's one like this. This is Beta Pictoris. It was discovered something like 10 years ago now. And here you do have an actual planet. So here you have the star right here in the middle. And Beta Big B, this little dot here, that is actually the planet. And the reason you don't see the star is because we've tried very hard to cancel it out because the star is very bright. But with instruments, we've tried to ignore the star and just look at everything around it, and you can actually see the planets, and you still see some of the disk. So the system looks like this, going around it. So there is a few images of a few planets like this where you actually see the light of a planet directly. Now, what do we know about this system? Anyone? No, I should probably. They're actually the disk, so they're material from the disk. So this is a very young system. So this is like? Yeah, so it's like this. So you should look at the disk like this. So this is a very young system where you still have a disk of material that's being formed, and with the planet pretty much somewhere here. Now, there should be a scale to this. No, not really. But this planet's about something like, I should check what I say, but something like 20 AU away. So it's, you know, it's pretty far out. When I say 20 AU, does that make sense? Yeah, 10 AU. All right. So it's an orbital period of 20 years. So it's pretty far. I mean, it doesn't look like it on this picture, but it's pretty far away from the star. And that's because it's really hard to find the ones that are close in, because there's a star. So we have other images like this. I'm going to show you another little movie here. So this is again a star in the middle, right there, where all the starlight has been cancelled out, and then there's now different planets around it. You see how many? So I'm going to show you the movie. So you see how this, let's take some water here. Is that fine? So you see the planets, how many? Ah, you had the previous course on lensing. Yeah, so. All right, so what you should be seeing here, I mean, this is a star, and you see some of the light of the star still, that varies here. Just because we're trying to cancel out all the light of the star, but it's really hard. So this is just the star, and normally this would be very bright, but we're canceling out all that light. And then there's one planet here, one here, one here, and one here. Right there. All right? And so again, here's the scale. This is 20 AU. So again, these are all, you know, very far away, very long periods.
I don't get how can we see the planets. Are they behind the star and we get the... Yes.
No, this, we're pretty much seeing this thing here. So we're looking at this from here. We see the star, and we have the planets around it, orbiting pretty much like this.
Okay, thanks.
So normally, I mean, one of these images, so an original image would just give you a planet here and a planet here. And the reason we're making this is because we're putting together data from different times. So there is a time scale here which goes between somewhere 2009 to 2015. And so you see the planets move over that period of time, and people have put this together in an actual movie that shows you how this looks like. But so even on something like 6 years' time, you see those planets haven't moved very far because they're very far away from their star.
Sorry. Do this like to block out the light from the star? Do they use like some physical object in the telescope, or do they edit it like after?